Okay, good morning. So now we start this third lecture of David on the machine learning.
Okay, thank you. So welcome back. So this is the third and last lecture, and I know. I have to click once.
Yeah.
Voilà. Voilà. Okay, so this is the third part, where on one side I will give more basic training tricks, and more advanced stuff on, for example, surrogate models. And I'll finish with a recommendation for machine learning software and tools, because I had a number of questions in the coffee breaks. So a very important thing in machine learning is that there is no miracle. There is no miracle for machine learning, no miracle for artificial intelligence. Things work, but it's not. You don't expect to just plug things and have things run magically. In particular, if you have two distributions, one for signal, one for background, and if you know the distributions, exponential, Gaussian, whatever, then there is a so-called Bayesian limit, which is the ratio of the likelihood, the ratio of the likelihood of the two function. This is the best discriminator you can have, okay? And so if you cannot beat that, so if the two distributions are not well separated, you will not have a very good result, and machine learning and not machine learning, it will be the same. So since we can get the best discriminator from the likelihood ratio, what is all this stuff about machine learning? The thing is that it's quite rare that you know the distribution exactly. It's rare that you know that the distributions follow an exponential Gaussian with this and that parameter, and so the machine learning, the whole point of machine learning is to learn the distribution. Remember also that I often do a simple drawing like that with x1 and x2, which is the dimension of the input. But for images, for example, the dimension of the input is a number of pixels. So 10,000, maybe 10,000 pixels. So it's difficult to think in a space of 10,000 dimensions. Nobody can do this. So we do these drawings in 1-2 dimension to try to understand things, and this is quite useful. But one has to realize that in reality you deal with a space with a much more dimensions. I will show an example of how this can be puzzling towards the end of this talk. So in summary, so if you have good reasons to believe that your measurement should follow, for example, an exponential distribution because it's a Mion decay, then you should not let the machine learning algorithm learn about it, but you can tell the machine learning algorithm. It's very similar to what we said. I said yesterday about feature engineering. So if you know you have 4 momentum, you know as physicists, you know that when you have 4 momentum, you can make invariant masses, and you should not have the machine learning algorithm discover that invariant mass is a useful concept. You have to tell the algorithm. Okay, I think I've stopped using this. A very important concept in machine learning is, I just alluded to this first lecture, is under-training over training. So, and again, I come back to a very simple case of curve fitting, this time in one dimension. So you have x and you have a y depending of x, and as you know, if the white curve, if the green curve is what you want to evaluate, if you have a model which is too simple, like a straight line, okay, the model doesn't go through the data. If you have the right model, it's okay. Then if the model is too complex, here it will try to follow every possible wiggles of your data, and this will be overfitting. This is not the reality. So this is called the problem of generalization, that if you have this curve passes through all the points, but if you have another experiments, then the spread of the points will be different, and it will not work anymore. And it's the same for machine learning, or now we go in 2 dimensions. If you want to separate population, X1 and X2, you clearly see that this one is not physical. So if you want to separate this region with 1 neuron, 2, 3 neurons, 5 neurons, 50 neurons, you see that the shape of the boundary region becomes more and more complex. So this is probably about right, but this is clearly wrong. Here you see that it has tried to isolate every possible blue point, and clearly, if you had another distribution, so another measurement with following the same distribution, this will not work at all. So the wet training is really common for all, even machine learning or all the fits which you want to do. And the problem is when the model is too complex with respect to the training data which you have. The complexity of the training data of the model cannot go beyond some amount of training data, and there is no rule which tells you, okay, I have 10,000 events, what can I do? You really have to try and to see. And there is technique to control the overtraining. I will explain just now. So that's a very nice all-in-one plot. And there is even a GitHub which shows how to reproduce this. So this is a problem of classification in a very simple case. And the vertical axis is the performance of the classifier, and the lower the better. Okay. So there is 2 things which are measured. One which is the measurement on a test set, and then the measurement of the training set. Okay, so the algorithm is trained on the training set and then evaluated on the test set. I will come back to that. And then when the model gets more complex, here is the number of leaves of boosted decision tree. If the model gets more and more complex, then the error goes down. Okay, and then for the training sample, it goes down until it reaches basically 0. It's equivalent of having the curve going through every point in what I've shown before. While the error on the test set improves, and then there is some optimum, and then it decreases a bit, but it doesn't, basically a plateau. And so when you see this, you say, okay, I'm going to stop more or less around here, because from here, I make the model more complex. It means that really my boundary line is going to go around all the points, but it doesn't improve. And here we will be in overtraining regime. And so if you now do a projection of the score, so typical score with the signal on the right and background on the left, and one has to check that the distribution of the score on the training sample with respect to the test sample. So the test sample is one on the red. So the distribution do not have to be exactly the same. That's very important. In the old days, it was taught that the 2 distributions should be exactly the same. That's not correct. The 2 distributions can be different. So it's expected to have different results on a training sample and a test sample, but it should not be too different. Okay. This corresponds to the optimum is here. The optimum is not there while the 2 curves start to disagree. And that's the correct one. So the same curve, larger. So you have the training test. The test is the plot. The training is the line, and here it agrees perfectly, but it can disagree. And but this curve should always be looked at. For example, there's a real life experiment where we see this. In some cases, here the blue is the background, and in some cases the background was given a perfect score of 1. And this was in fact a bug which was related to handling the negative weight event. So in physics, some case we have negative weight event which never happens in the outside physics, and it's always a problem. And the software which we use is not always used to treat with negative weight. But this is already a curve. It means this is a curve which has to be checked all the time. Cross-validation, this is related to this. So what we do usually is called one-fold cross-validation, which is, okay, you have a sample, you divide in 2, and then you train on one half. It could be more than one half. It could be 80%, 20%, whatever. But at least you train on one part and you evaluate on the second part. And if you use TMVA in root, this is the default, and this is the simplest we can do. So training sample and test sample. But you can do better, which is really the point of cross-validation. Here is two-fold cross-validation that you train on A, you test on B. But then you can also train on B and test on A. Okay, and A and B are completely equivalent data, just different instances. And the point with that is that this way you can measure on the whole sample the statistical error on the measurement of the performance of the algorithm is obtained from the full sample. But then you have trained only on half of the sample. Okay, so then you can do even better, which is five-fold cross-validation, where you will see the ID. You separate the sample in 5 pieces, and then you train on A, B, C, D, and then you test on E. And same story. You get the ID. You always train on 80% of the data, and you test on 20%. And then when you put everything together, what you have done is you're still testing on the full statistics, and then your training sample is 80% of the original sample instead of 50%. So you could go 5-fold, 10-fold, 20-fold, but at some point there is a diminishing return, and 5-fold is what people do usually. It's a good compromise. There is still something which is more sophisticated which can be done. It's the following. The problem with this approach is that you have to do 5 different training, okay? And on 80% of the data set, and which can take time if it's a neural network. So what you can do is to train separately on A, B, C, D, E, and then instead of retraining on 80% of the data set with different 80% every time, you have one training for each part, and then you combine them together with some kind of average. And here I put average in quotes because it could be arithmetic average, it could be median, it could be a different way of combining the score. And for some reason, this in fact provides the best performance in some cases. It's really I didn't say that in the beginning, but machine learning is a very experimental science. That the theory is always behind. There are people trying many things, and then the theories they say, okay, this works because blah blah blah. So probably why I like this very much is that you it's very hands-on. You have to experiment many ideas and then see what works. So another point of cross-validation. So you have split your data set so in A, B, C, D, E, and then you can train on one, test on the other. So you can fill the matrix. So as mentioned several times, and we'll come back to this many times, the results on the test, the test result on an algorithm which you have trained on the same data set is really meaningless. So you should not look at the result of the testing on the same data set as training. So this diagonal should not look. But then you can fill all these metrics. And then on one side, you have, when you combine these, you have the testing variance. And the other side, combine these, you have the training variance. How much your algorithm depends of your training data set. And so you have information like that, which tells you basically what you could gain to have more data. And it tells you also if the algorithm is too complex or not too complex. In summary, so what should be done? So you have a data set. You should foresee from the beginning to separate the data set into a training and testing data set. And even the training is further split into training and validation. This is because of something which I will come back to that called hyperparameter optimization, meaning that it's not like you have the algorithm, you train and you have a result. You have to optimize the internal parameter, which are called the hyperparameter. You have to you have to optimize this hyperparameter. And this you do on this validation data set. And voilà, in part, ideally, the testing data set, it should really be look only once at the end. Otherwise, it will be slightly wrong. The problem is that this is fine to do this when you're working on your own, on your data. But as soon as you're working in a large collaboration, it's more difficult because you will do the training, and then the same data will be used by the other people. Okay, and this makes things more difficult. So I really want to insist that you can get better result if you testing on your training data. Everyone knows this, but this is an horror story which happens many times. For example, there was a report that an AI was working very well, but because at the end they realized that in fact they were using the training data set to report the result. But also in physics, there is internal story in the collaboration. For example, I can tell one in Atlas, but I'm sure things like that happen in CMS as well. I was in an editorial board of a paper, and there was a result which was looking strange, but the result of BDT, it was a simple BDT. And it turns out that the people who have trained the BDT, they had split the data set randomly, because there are tools to do this very easily. But then they have not kept track of which data was used for the training. So they did a proper job, training versus testing, but then the person optimizing the algorithm gave the results, gave the BDT to somebody else doing the full analysis without telling him which data set was used for training. And then the result was wrong. And then they had no other way than to regenerate new Monte Carlo to be able to evaluate the performance of the algorithm in an independent way. And there are many stories like that. So never test your algorithm on your training data. That's the one thing you should remember. Learning curve is a very useful concept. So it's very simple. It's not used as much as it should be. It's very simple. You have a performance measurement. It could be the AUC. It's better to have the significance. So significance is a number of sigma of your analysis, and the higher the better. And this curve shows the significance of your classifying algorithm as a function of a number of events used for training. And the significance is always evaluated on the same test data set, but then you increase the number of events for training, and then you expect the significance to improve and to reach some plateau. So it's very interesting to see the behavior. So this is for a simple example with running a BDT, or no, not a BDT, running a classifier on 4 vectors in a Higgs analysis. And the blue is XGBoost, which is a popular, I will come back to that, BDT algorithm. LightGBM is another popular BDT algorithm, and neural network is a simple neural network. And you see the 3 increase quite a bit, quite very fast. And then it seems the blue reaches a plateau, meaning if you have more events, you will not improve. XGBoost reaches a plateau, while LightGBM and neural networks continue to increase. So the behavior for neural network I was expecting was, I mentioned this yesterday, neural network needs much more data to train than BDT. And then you keep adding events, training events, and it keep increasing slowly, but if you add more events, the plateau is reached much farther. So the more data you have, usually the better the result. What was surprising to me was that LightGBM, which is another BDT, had the same behavior. So it's a very useful plot to look, because you can see if you, well, here you can say, okay, maybe if I have more data, I will still improve with LightGBM on our network. But if you stop here, you clearly see, okay, I need to have more data. It will tell you if you need more data or whether it's not necessary. And voila. So the 2 important things to look at is how fast is increased there and whether a plateau is reached. This leads me to hyperparameter optimization, which is commonly labeled HPO. So any algorithm have internal parameter, not the weights of the neural networks, not the tree itself, but the parameter which is used during the training. And what it should do is to try to find what are these hyperparameters, to optimize them, and then to do many times, for example, this performance curve to see which one is the best. And for example, this is for a BDT. Yeah, again a BDT. IMS is again the significance, so the higher the better, as a function of the number of trees. So it's a boosted decision tree where there is a combination of many trees, and the depth of the tree. So how many steps do you have in the tree? So depth, red is a tree of depth 2, yellow is 3, light blue is 4, dark blue is 5. So you try different values. So there is a way to do it semi-automatically. And then we clearly see at the optimum. So of course there is some statistical fluctuation in the result. So you have to smooth the function at least by eye, and you clearly see that somewhere here, meaning with a depth of 3, with a number of trees of 500 is optimum. Okay, compared to other results. The very nice thing about BDT is that there is little HPO to be done. Usually, despite what I said, usually you just run XGBoost, for example, and it just works. And then you can improve a bit with HPO, but not a lot. With neural network, the space of parameter to be optimized is much larger. There are much more possibilities. Plus, one training with neural network takes more time. So overall, the HPO optimization on neural network is much more takes much more human time and computing power than BDT. So it's another good reason to stick to BDT for simple case. Another good reason to start with BDT whenever you have something you want to start with machine learning. Okay, now I move to more complex stuff, which are surrogate models. So AI and machine learning can be used to make things better, but there is something which is less known, but very useful, is that it can be used to just to do the same thing, but faster, even much, much, much faster. So surrogate model means you replace an existing model with a model based on machine learning, which you expect to be run faster. So this comes back to the universal approximation theorem, which I mentioned at the very beginning, which is that, in short, a neural network can emulate, it exists neural network which can emulate with arbitrary precision any model y equals f of x, and x and y being of any dimension. This neural network exists if properly trained. A simple real-life application from a colleague in my laboratory. She was working on a camera which is designed to. She's working on medical physics. It's a camera which detects beta and gamma to help a surgeon during a surgery. So the person is injected some radioactive element which goes into specific places, and the surgeon can look at these places using this handheld camera. So these are crystals, and then when the gamma hits the detector, then there is a signal which is not just one crystal, but several crystals are touched, and this is the image for one gamma. And the question is, okay, now she wants to reconstruct 2D images, taking into account how the energy from the gamma is spread over the crystals. So if this is done in a naive way, just taking the barycenter of the different measurements, one gets this image. This image is an accumulation of calibration points. So when moving a laser on a grid on the camera, this is the image which she gets, which is inaccurate but fast, because simple barycenter. There is an original algorithm which is called Levenberg-Markov, which is an iterative algorithm which works well, more or less reproducing the matrix grid, but is very slow. And then she has worked on emulating this algorithm with a simple dense neural network, and with getting this result, which is both as accurate as the previous one, but much, much faster, because neural network, once it is trained, it's just a simple linear, not just linear, but almost linear algebra. And this can be implemented into chips, because this has to run online, because you really want whatever happens on the camera to be displayed on a screen online with a, I don't know, 20 hertz repetition rate. And this worked very well. So it was really a matter of emulating a function which is a 16 times 16. This is the number of the dimension of x, and y. The output is a 2-dimension position in the plane. Okay, now a much more complex thing. So these are generative models, which was already has exploded a few years ago. Here it's generating an image of a person which does not exist, and changing the parameter of the person. You can select male, female, if she has less or more hair, if she's smiling or not. And so we want to use something like that. I'll tell you why. This is for simulation. So we are using a lot of simulation in physics. We are using GN4, which is gives very good results, but which is very slow. And in particular, for at the Large Hadron Collider, we are running on the grid, which is a set of computer which is distributed all over the world. And last I checked, there are 1 million CPU core and half of this core are working on delivering simulation for mainly Atlas and CMS. And we are going to take more and more data, and to analyze this data, we need more and more simulated data. And we cannot use more resources than what we're using right now. So we have to speed up this simulation. And so what we are working on is the following. So we have, if we concentrate on just simulating the most time-consuming part is simulating a shower. So as an electron incoming the colorimeter, which generates photons create electron. This is a cascade of particles down to the lowest energy electron, which is what is measured. And so we want to emulate this shower with a simple neural network. So the technique of the GAN is to say, okay, I have a neural network here. The input is just random noise, and the output should be an image, meaning by image, the distribution of energy in the colorimeter cell. Here, conceptually, the cell, each cell is a small cube. So I have this generator neural network, which will just emulate these images. And then there is a second discriminator, which will analyze both the GN4, which is supposed to be the real truth, and the generator images, and they will try to separate the two. And the two are trained together, meaning that the discriminator will force the generator to create images which are as good or similar to the one from the simulator. And then when it is trained, same story, we will still use the random generator part here, the white noise, and use it to generate the cells. And then since the neural networks are very fast, this allows to speed up the simulation by 3 or 4 orders of magnitude. This is what we want. So this bit more detailed. The Atlas colorimeter is very complex. Electromagnetic colorimeter in CMS, they are full crystals which have no structure. It's very, very nice. In Atlas, this is the liquid argon calorimeter with an accordion where the liquid argon is, and then the cells have a different structure with different size. And one has to simulate the energy deposition in these. And so the two neural network, one is a generator, which takes some white noise and creates the shower. And the second is a discriminator, which tries to separate the one generated and the one from GN4, which is taken to be the real one. And long story short, after it's maybe 6 months of work to have it work and training and so on, these are this typical energy, like energy of in the layer 1, layer 2, in layer 3. Comparing GN4 with GAN and VIE, which is a different technique for generator, and it kind of works, but still more work is needed. And this has just been published as it has been released and not yet fully published by Atlas. I skip this. Okay, so we started working on GAN when they came out in 2016-17. And there have been a lot of development, and you've heard probably of DALI. DALI, you put a prompt, espresso machine that makes coffee from human cells, Panda mad scientists mixing sparkling chemicals, and then you write a prompt and it generates an image with high quality, with the quality which is unmatched compared to what was done before. And this is based on a diffusion model, which is a completely different technique. And so a colleague from Berkeley, they've tried something simple to see whether diffusion model can be done, can be used to generate, to simulate detector. And it kind of works to see distributions. The problem is that for the diffusion model, even when you do the inference, meaning when you run the neural network, you have to do it in iteration. It is relatively slow. So instead of gaining 3 or 4 orders of magnitude, you will gain only 1. And then it's not clear that whether it's also used a lot of memory as well. So it's not clear whether in practice it will be very practical. Okay, another use of GAN is called for style transfer. It's called. So you have a photo picture, and then you can change it into a painting. Now you have this on your phone probably, and if you have a painting, you can change the color that it looks like a real picture. This was funny. They took a conference. They look at they separate the paper which was accepted in the conference, paper which was rejected, and then just run an image algorithm on that, and to try to see whether they can separate the bad paper and the good paper, and then it can change the bad paper and the good paper just by changing the layout, and vice versa. This was a kind of a joke. Another thing which is really amazing. So this is a zebra and a horse, and one is real, one is fake. Do you know which one is real? So who says the horse is real? Who says the zebra is real? Okay. Now, if you look carefully, the tail of the zebra. First, the zebra has a very short tail. The tail of the zebra, the stripes are really always changing. Okay, so it's really a horse turned into a zebra, and here it's I find it even more interesting. So this is a winter landscape, or from dash camera, and a summer one. So one is real, one is fake. Can you guess which one? So who thinks the winter is real? Who thinks the summer is real? Okay, look carefully. In the summer one, it's the winter which is real. In the summer one, sometimes it tries to add some branches to the poles. Okay, because it cannot say, it cannot differ. If there is a pole, maybe it's a tree which is has no leaves, so it has the branches on the poles. Okay, so it's really fascinating because the algorithm has never seen other images. It was trained on a dash camera from both winter and summer, but on different road, and then it can extract the kind of style, and change the style for this. So what can we do with this? Just not to have fun. I mentioned that we have a lot of using a lot of simulation. So this is the CERN Computing Center, but it's running on the grid worldwide on millions of cores, and we're using data to do analysis, and we always have the problem that the simulation is not quite as like data. So this technique can be used to turn your simulation, to change it a bit so that it looks really like the data. Okay, another thing is called adversarial example, but it's nothing to do with the generative adversarial network. Even it's the same person who has discovered it. It's something which you might have heard as well. So you have an algorithm which classifies images, and then you can add very subtle differences, some noise, and change the identification to a tabby cat, or even to a trombone, something completely different, just by adding some subtle differences. So this is really quite interesting because it tells you first that okay, a machine learning algorithm does not work at all like the human brain, because of course this does not fool any human, and it still fools an algorithm. So we were a bit worried about this. It's again a story about interpolation versus extrapolation. So I mentioned this. So here, if you testing your model within your training points, you're interpolating, and then you cannot be too wrong. Okay, but then if you're testing your model outside your training, you can get something which is completely crazy. So this is simple in 1 dimension, but already in 2 dimensions. So if I have this distribution, if I move along the green line, clearly this is interpolation. If I move along the red arrow, it is extrapolation. But now if I'm there, this is interpolation or extrapolation, I don't know. And remember, images are in a space of 10,000 dimensions. Here already in 2 dimensions, it's not too clear. So it's really the key that we are in a space of 10,000 dimensions, and the way the machine learning algorithm works is navigating this space in a way which is very different from the human. Another example is an algorithm which detects a person, and then just by holding this picture, the algorithm is fooled. Do not see this person, and there is a nice video where the 2 guys, they're just manipulating the picture, and then when this guy gives the picture to that, suddenly he disappears for the algorithm, and he appears. So what if something like that happens when we are analyzing our data? It will make Higgs event appear or disappear. And the key thing is that this adversarial example is really like an optical illusion for neural network, and what is done is really to in the space of 10,000 dimensions is really to move in a very, very, very specific way. So the chance for this to happen by chance is infinitesimal. Okay, and so this can work only if you have a deliberate intent to fool a DNN. Like if in Atlas, I could access the CMS data and then change it in a way, and then CMS will say, I have discovered, I don't know, the Z prime. That would be the only way that something like that happens. But it cannot happen by chance. Okay, I'm wrapping up. So the three hours of courses. So the machine learning playground. So we have what we are doing as physicists. We take data. When we do the analysis, we have to design a detector first, but we take detector is designed, and then it's running. We have data, and now output this paper. So at the beginning, we were using, I mentioned this, machine learning mostly to do statistical optimization of an analysis, like we did for the Higgs boson, where we gained 20%, 25%. But then more and more, this has been used for particle identification, electron ID, tau ID, more and more for trigger optimization, and this is a big thing for the run, which is of the Lachi, which has started just recently, and even bigger for the last run of the Lachi after the grade, which will start in 29 now, I think. We can do regression. Didn't mention that. Classification and regression for a neural network algorithm is really the same. It's just the function to be optimized is different, but it's really the same architecture. You can regress instead of classify. And then we have detector simulation, the generators optimization as well. And something I'm working on just right now is to, instead of just optimizing the statistical algorithm, also optimize the systematic part of the analysis. Okay, some of you ask me, okay, I want to start with machine learning. Where do I start? So my advice is really to, there are machine learning school for high energy physics. The thing, if you look at the web, there are a lot of resources for machine learning, but in many cases, it will not be relevant to do physics. So the best is really to start with schools which are about machine learning for physics. It's a full one-week school. There is one which we have done in France, but it's in English this last spring. It's called SOS 22. It has the slides, the recording, hands-on exercise. There is a one which is called HepML School. So I don't know who asked about it. The one which has was in Lausanne in 21. There is nothing. Fortunately, on the Andy code, there is nothing. And I sent a mail to the person organizing it. I had not replied, but if he replies me, I will update the slide. And there will be one in April 2023 in RHA. It's a bit more advanced than the what we do in France. So we suggest to start with the SOS 2022, and then this one. And this one in RHA in Italy, and I'm not sure about remote participation. And again, I've asked the person about this. Competing resources, I must say I don't know the status in India. What resources do you have access to? For sure, already with the laptop and simple computer, you can do a lot. You've heard about, I don't know, ChatGPT on their own using thousands of GPU. Our problems are much more simpler in terms of amount of data, etc. So you should not, in general, it is not. You should not be blocked by that. Maybe there are GPU around some place to do something a bit more complicated, but already having a laptop is a good start. Nowadays, there are many papers which are released, which comes with there is a GitHub, so you can which you can use, and when it's well done, you can already run immediately the code which is used to do the plots in the paper. It's very useful. There is a book which I edited. This is I spent much of the first year of COVID working on this. Unfortunately, it's not my fault. This is very expensive, but many chapters are on archive. So if you look at the book, it's really interesting because machine learning for physics has been around since 2013, 14. A lot of developments. So it was time to capture this development and make a book, even though things are evolving quite a bit. But for example, here there are chapters on BDT, of course, on graph neural network, on generative models, etc., etc. So it's really we recommend to look, either have the book or look at different chapters and to find them on archive. And even if you don't see the chapter on archive, if you send a mail to the author or to me, I can send you the PDF. Voilà, machine learning tool, another discussion which we had here, using root or not using root. So root is it's a standard in physics. It has been instrumental into democratizing machine learning at LHC at the beginning. And in root, there is TMVA, which is the library of machine learning algorithm. The thing is that it's really not up to date compared to latest development. I mean, there are millions of people doing machine learning, developing BDT, neural network, and so on, and we cannot compete with them. So I do not advise. I really do not advise to use TMVA. Rather, there is something which is very nice. It's called uproot, where you give an n tuple, and then you read it in a pandas. You read it in a NumPy array, and then you're in Python with NumPy array, and you can use matplotlib, scikit-learn, the whole ecosystem, and use it from there. There are few people who are using less and less people using MATLAB. MATLAB was popular for machine learning 2 years ago, but it's really quite limited. So we really not advise MATLAB. Everyone, more or less, is using the Python ecosystem. Not in passing, again, a discussion during the lab visit is that to do proper histogram fitting with proper uncertainties, root is still better than SAPI. in one line, you can do proper fit, and SciPy is you have to do it yourself, more or less. And this is because, unless it has changed very recently, the concept of histogram is not of weighted histograms with error bars, which is kept and memorized when you scale them, is done only properly in root. It's completely native, completely standard, while you more or less have to do it yourself when you work with SciPy. There is a group called PyHep, Python HEP for energy physics, which are doing many developments, including this uproot, which is very nice. Unfortunately, they are not working on these kind of things. Why it would be very useful. Okay, SGBoost is really a very popular algorithm. In fact, this was originally delivered for the XML challenge. So organized the XML challenge where I put on the web data from Atlas with a Higgs signal versus background. And this was then released on Kaggle, which is a popular platform for machine learning. And then XGBoost was released for this opportunity. And then it has become the de facto standard for BDT. And it's the nice thing is it's very fast. It's very fast, plus it's well supported, plus it gives good results immediately. You can do some optimization to gain a little bit of performance, but already just you're running it as it is, give you very good results, both for classification and regression. And as I said many times, it's much easier to start with BDT because it's very fast training and simple to tune than to start with neural network. So I always advise to start with neural network, and quite often to stay with to start with BDT, sorry, and quite often to stay with BDT when the problem is simple enough. Scikit-learn is a toolbox for machine learning in Python. In fact, it was started 10 years ago by people in Paris-Saclay, but now it's used everywhere. There is the Jupyter interface, which is a notebook, La Mathematica, but now people know more Jupyter than Mathematica. It interfaces very well with NumPy, SciPy, Matplotlib, and it has all the major machine learning algorithms except deep learning. This is deliberate. There is no deep learning in scikit-learn, but everything else, all the support for deep learning is there, and the doc is very nice. But it's really quite different from root MVA. If you're used to root MVA, you move to scikit-learn. Okay, it's really not done the same way. Neural networks, there are two major libraries for neural networks. One which is TensorFlow, and used to be Keras. Now Keras has been integrated into TensorFlow, developed by Google, and PyTorch developed by Facebook Meta. So both are completely free, open source. And very important, both can talk to the GPU on your laptop with, in principle, minimal effort. Although sometimes there is installation is not trivial because the CUDA, which is the part making the interface between the GPU and the code, has to be tuned, installed in a proper way. But these are the two. And which one is better? Myself, I use TensorFlow, but because I started with TensorFlow. Other people use PyTorch. I'm very happy with PyTorch. There is really no, you should pick one and know it very well. Okay, I'm close to be finished. Machine learning for physics, why is it special? So the things to remember if you look at machine learning tutorial or courses which are generic, not for physics, you should realize that for physics, things are special. For example, there are many things in machine learning outside, which is about analyzing images, but we very rarely have images. I have colleagues which work on telescope to find dark matter. This is okay. They have images, but it's rare that we have images. Also, we have very good simulation. That while there is no good simulation of a street with cars and so on and so forth. So we have very good simulation, and with the simulation, we have in the simulation, we have what is called the ground truth. So we can say, okay, if this event is really a Higgs boson or a TT bar or whatever, this particle, is it really an electron or a tau or whatever? And this is quite often not really the case outside our community. We do have very, very large data and very detailed models. So we need to go fast, which might not be the case elsewhere. And also we worry about uncertainty, both statistical and systematic uncertainty. We don't quote just the result, we quote the result with uncertainties, which is usually not the worry in courses, generic machine learning courses. It also means that to do some analysis till the end, we cannot just take something on the shelf and just run. We really have to understand the details. And another thing is that the developments which we are doing in high energy physics, where we have a long history of doing big data, even if it was not called big data, they are relevant for other sciences, which have only recently started with big data. And finally, so in high energy physics, so we are analyzing data sometimes from multi-billion euro or dollar projects, so the Atlas and CMS experiment. So we should really make the most of it. If you gain 25% statistics on an Atlas analysis, you realize that okay, it's equivalent to run the LHC for 1 more year. It's a lot of money. And so there is the explosion of a lot of new machine learning techniques. Sometimes they are easy, many times they are complex. But we have a lot of open source software, something which I like very much when I went into machine learning. Everything is open, software is open, a lot of publications, which is natural for physics, but not natural at all in the private industry. And there are a lot of resources on the web. So finally, if you have a big machine learning idea, a great idea, first you have to demonstrate on a toy dataset, something very simple, then demonstrate on something a bit more complex, then demonstrated finally on the real experiment dataset, and finally publish using this all this. So it's there's 5 steps, and quite often we see a lot of papers where they stop here, and then they go to a different problem, and again they do a paper at this level. Well, the goal is really to go to the end, to have publications with physics measurements using maybe machine learning, but one should really have the objective at the end. What we want to do is physics with machine learning. Okay, thank you.
Any question?
Thank you for the nice present. Yes, it's audible, right? So my question is, usually when we train a model, we need to have a good idea about the physics, underlying physics, and then we can train our model. Have there been any attempts to do the other way, means to get patterns out of physics and data and then make some physics model out of it?
It's a very good question. I have in mind a paper where they look at identifying electrons in the calorimeter. And what they could see is that using a neural network is that the results they obtained was clearly better than the traditional technique. And then they managed to say, okay, this is because the traditional techniques is missing. I'm just making this up, is missing, for example, some information on the longitudinal spread of the shower. So they could then invent a variable like the longitudinal spread and add it to the traditional technique, which is discussion based, to make it work as well as the machine learning. So in this case, it does happen that you can use machine learning, in fact, to give you idea where in the space of features, where the separation, for example, between data and background is the best. So yes, you're right. This can be used in this way.
Thank you.
Okay, thank you, David. I had a question about the BTT score that you showed in slide 9. You said that there is a bug in the training. So I was wondering, you said it's due to some negative weights. How do you usually handle that? Do you have to identify this event that has this high negative weight and then you remove it, or how is it handled? And my second question is about the hyperparameter training. You showed the plot with different results, like different entries and max depth and so on. So how could you tell which one is better to be used?
Okay.
Thank
so
you.
first on this, so negative weight is really whenever you have a tool, machine learning coming from whoever, the negative weights are even scikit-learn. Scikit-learn, there are some algorithm which works well with negative weight, some which would just crash. Okay. And it is really a problem. So one really has to try. You can maybe, if you have a few negative weight events, you can remove them for the training. You can do this, but of course, for the testing, you should always have the negative weight, otherwise your evaluation would not be correct. So it's something to be tried, but there is no general rule. It depends on the algorithm which you use.
Okay, and how can you say that this is due to negative weights?
Because we have investigated. We look, okay, selected this event. What are these events special? And then okay, so they all have negative weights because we had the list of events, and we could find all the events which was there just by investigating exactly what was going on.
Okay.
And then, but then there was the question about it's really so to optimize the HPO. There is the simple way is to do there is in scikit-learn there is a automatic grid search, or I advocate using random search. So you say, okay, I want to optimize this parameter in this range, that range, and it takes basically it runs iteratively. And you basically for each set of parameter, you have the results on the test, and then you take the highest. But you have to kind of fit by eye because sometimes you have fluctuations. So that's the way you do it. There are more sophisticated way to do it with a Bayesian approach, etc. If you really want to optimize, for example, neural network in a very the space of parameters is much larger. It's more complex. There are algorithms. Some are built into TensorFlow, I think. I've not used them to really only do the hyperparameter optimization. There are algorithms to do this. But the simplest thing to do is really to do a grid search or random search and just find what is the best combination.
Okay, thank you.
Yeah, very nice talk. So this point, of course, is well known, but just I wanted to get your views on it. Normally, when you do physics analysis, you also, most of the time, along with the results, you will, of course, say how you arrive at the results. And also, more importantly, you give the uncertainties, the error bars, the confidence levels, and so on, which I guess, I mean, generally a bit difficult in the current system, the learning systems. So I'm not sure if you have covered this, but I just wanted to know how these are being implemented in the learning system.
I'm not sure I understood completely. So what has to be done is really to you try on simulation and you apply on data. It's true that you don't just apply on data and see the results. You look at many distributions of the score, for example, to compare the distribution of the score in control region. So not in a region where there is data, but in control region where we expect there is no data. Here, the score should match, the simulation should match the data. If not, it means that we need to improve the simulation. But and if you cannot improve simulation, you can just use the algorithm, because it's true that the machine learning algorithm is relying more on simulation than something which is much more simple.
Okay, yeah,
Let's
thanks.
Stop here the discussion. Yeah, this is the okay, David, thanks. There's lots of question and answer that tells that how the people are interested of this. And again, this is the same thing from the institute. I'm trying to give you this
Thank you.
collection of the institute.
Thanks a lot. Thanks a lot.
Also, this is our small painting. This is our local people, local painter.
Okay. Thanks a lot, and many thanks for the invitation. I've enjoyed it a lot.